Hello, this is Carson Granja with Appalachian State University. Today we're going to be going over two major practices and uses for BIM, or Building Information Modeling. Without further ado, let's get started. So building information modeling is a complex computer program, and it pretty much helps designers, engineers, and all kinds of building scientists to construct buildings with incredible accuracy and detail that is not humanly possible. There are dozens of different BIM-related softwares, including but not limited to AutoCAD, Revit, SketchUp, Energy Plus, and others. The concept of BIM has been around for a while. It's existed since the 1970s. The first practical software were developed in the late 70s and early 1980s. Included things like workstation products, Chuck Eisman's building description system, Glide, RuCaps, Sonata, Reflex, and Gable 4D series. All of these were essentially to help architects with drafting in a more efficient and accurate way. I would say between 20 and 30 draftsmen could be replaced with one guy and a mouse. So it was very revolutionary at the time. Going on to uses and practices. BIMs are used around the world to facilitate environment in which design and construction terms can effectively build structures for clients in a way that allows for the best possible product. Computer modeling allows for a level of precision that just isn't humanly possible. These softwares also produce models that allow any team to access the said model in real time. And there are many functions that these models have allowed building teams to execute without ever being in contact with one another, which in recent times has been more critical than ever. These programs give teams flexibility, creative thought ideas, and things that simply wouldn't be practiced with pencil and paper. So categorical uses. Building modeling has advanced to the point that almost every single category of construction can be assisted by using it. And what I mean by that is the 33 different sectors of construction, anywhere from 0 to 1 pre-existing conditions all the way to 33. The following just is more insight on how this is possible to use BIM for two specific purposes related to this. So using BIM for laser scanning. So this is actually a relatively new development, started around 2014, 2015. Build models can now use laser scanning in order to better understand the construction site, surrounding areas, and ensure a smooth construction process from the beginning. In past years, existing conditions were something that were taken by recordings, photos, and by word of mouth even, to get the project started off right. But this, of course, has a lot of human error, and people get lost in communication. So pre-existing conditions, anything from existing structures, pre-existing foundations that have never been demolished, any kind of utility lines running underground, electrical, plumbing, water lines could have been disrupted during the construction process, and trying to use laser scanning in order to better precisely keep a detailed record of these areas tries to prevent things like that from happening. It also allows construction teams to work more efficiently, best execute their plan of attack when trying to get into oftentimes crowded or surrounded sites. And it usually can also help with budgets and keeping budget constraints and time constraints, keeping projects on time. So there's a growing need for tools automating the process of as-built 3D laser scan data. More particularly, the comparison of this as-built data with planned works. Using this technique at this time can be considered somewhat high risk, high reward with BIM models. These scans initially facilitated with high definition photos taken from many different views or done with drones with cameras mounts. They are then uploaded into a software that turns these photos into functioning models. Like I said, these models have only been running on a large scale since around 2014, so these models oftentimes leave out certain details that can later affect the model. BIM software compatibility with such scanning. FarrowPoint Sense, Edgewise, and TruePoint are examples of software extensions that give normal BIM programs the ability to take laser scans, turn them into 3D models that can be edited and viewed to continue the project. These extensions use advanced graphing transfer data points organized into preset identifiers to understand what an image is displaying, and then allows that program to show the image as a model. This process takes a lot of human input to fix software errors, and to an extent the software is still somewhat susceptible to human errors in which people have to go in and fix such models. One other small problem I didn't mention on the screen, but these models can take massive amounts of computer storage, and oftentimes when trying to be displayed on small PCs such as the one I'm recording this video on, they can overwhelm the PC. There can be glitches, and sometimes the model fully doesn't load in a timely fashion. So we're going to look at a couple case studies where such scanning was actually very effective. And this is done on a very professional, high quality level. Advanced softwares were definitely used, in this case being the Deep Design Studio 3D. So the case study we're going to look at first is the San Francisco War Memorial Opera House. This project size was roughly about 12,000 square feet. And so the generic scope of work, it was a historic San Francisco War Memorial Opera House, needed to have the seating rearranged on the first floor to better accommodate for better viewing angles of different performances. An additional challenge that was also presented in some sort of a mushroom-like floor vent that could not be relocated in a new seating arrangement, and it could not interfere with we could not really interfere with said vents when this company was actually trying to rearrange the seating. So some results. The Deep Design Studio 3D surveyed the entire auditorium, this entire 12,000 square foot auditorium, and by capturing the vents under the seating in a data scan with advanced photography and cameras. This data was then processed and registered together to create a 3D model that could be inserted into in this case, a Revit BIM file. This allowed for easy modeling of the space and the seating and vents, as well as analyzing the slope of the floor and the current ADA conditions in the aisles were met. And it resulted in a successful project that finished well under budget. And so here are some of the photos of that. The one in the top left corner and the bottom right are actual photos, and of course the one in the bottom left and upper right are scanned photos of different angles of the Opera House. And you can see how by using these cameras and this high definition data software transfer method, an extreme level of detail can be achieved. Now, for a project that on any kind of residential scale, I don't think that this would really be applicable. But with a project of this scope and this size, you can see how using a traditional model with such complexity would probably take, a team a long time to assemble to a successful BIM model. So by using this kind of software, it really helped them get things moving, and the project was, finished in a very timely fashion with less resources than initially thought necessary. So we're going to look at another case study. These are the Northeast Collections retail space at Logan International Airport. This airport has roughly 40 million passengers traveling through it each year. Boston Logan International Airport is one of the busiest airports on the eastern seaboard. So the challenge here is that any busy site sees a lot of foot traffic, present challenges when 3D scanning. Obviously, you don't want things getting in the way, causing a distraction. People moving actually can affect the photos, and the scan simply won't come out right. So getting a scan at all in such an environment is not easy. It's an extremely busy airport here in Boston, with thousands of travelers arriving, departing, making connection flights each day, each week. Massport, the airport operator would not allow any impediments to their normal business flow. So that meant that any measuring activity could not disturb the daily activities of the airport or any of the travelers getting from different terminals, taking off, landing, and so on. So that was that can be a huge challenge. Again, one of the cons of trying to get this kind of software up and running. So the solution. Deep Design Studio was commissioned to help a facility project. Yeah, upon arrival, they took dozens of different scans, taken in color and HDR, registered actually the next day, which is pretty amazing. Had probably quite a good sized team working on this. Short week and a half later, Paul Lukacs, I want to say, architects received final Revit as-built model, showed not only the space but all electronic devices associated with the base, and as well as a built-in shelving and ceiling features. So by using this advanced Deep Design Studio, pretty much this company is just kind of sitting back and to a degree boasting that their data collection software, these scans, can even work with impediments such as people coming and going and being in and out of the photos that they're taking to scan, which is really has to do with some advanced motion detectors probably built in, and some background software that probably allows the removal of impediments from the photos so that you can still get a uniform scan of the area. And like I said, this company in particular has figured this out to a degree that they can actually run these scans even in a busy airport like in Boston. So the results here were in the case study is that the Deep Design Studio constructed a highly detailed model of the existing Northeast collection space quicker and far more accurately than was even anticipated. From there, the architect was able to quickly and easily integrate the scan data as-built Revit model in the design process. And the level of accuracy of the as-built model permitted construction to begin fairly quickly. I want to say when I looked at this, it was roughly 2 to 3 weeks later. High quality work also meant there was little to no charge orders on the RFI, and the process could continue smoothly. So again, these kind of laser, some people call it laser scanning, but really it's a 3D high definition advanced camera scanning that can then turn into as-built models and several building information model BIMs that you want to put it in. In this case, it was Revit, but I've also was able to find some less successful scans in SketchUp and AutoCAD. It seems Revit is the most compatible with the technology thus far. So that rounds off the first one. We're going to go on to the next. So the second use we have here is for structural analysis. BIM modeling in recent years has become practical to engineering firms looking to find better ways to analyze structure for quality control. And using recent BIM softwares, it is now possible for engineers to produce anything from material selection and beam sizing to shear strength related to occupancy limits for floor spaces and such. So we're going to look at a case study here. This is the Macquarie University Incubator in Australia. This is a 953 square meter completed space at the university, and it was finished in 2017. So this project set out with goals to be environmentally friendly and to use only local resources. That being said, the university incubator could only be constructed using relatively smaller pieces of local lumber as to larger size beams to support roofs, floors, and so on. So this presented a huge challenge as to how the structure could be capable to support itself. Well, luckily BIM has introduced a number of different static and dynamic engineering calculation load capabilities, and this called the engineering team to use, obviously this BIM to assist it in running a series of structural tests using beam size, span length, total weight of the structure above and below specific graphical selected points in the BIM model to figure out where the wall supports and other beams should be implemented and what size they need to be as well. So pretty much by using this structural analysis, the team was able to have a total of 11% saved wood, less board feet of wood that